And on to problem 5. So in problem 5, we're given this function and we want to find the slope. Now, it's going to be real easy for us to think of this as 3 times something to the negative 1 power, this 2x squared minus 7x plus 5. And I want to take the derivative of this to find the slope. My slope is going to be whatever the derivative is at x equals 3. So for us, it's going to be negative 3 times my quantity to the negative 2 power, 2x squared minus 7x plus 5, times the chain rule, 4x minus 7. And I'm evaluating this at x equals 3. So I end up with negative 3 times 4 times 3 minus 7 all over 2 times 3 squared minus 7 times 3 plus 5. And of course, this is a beautiful answer. I don't need to worry about trying to simplify this. It's probably not going to be very helpful for me to simplify this. Moving on, part B says find the x-coordinate of each critical point. Remember, critical points are where the second derivative, or excuse me, where the first derivative equals 0 or it's undefined on this interval from 1 to 2.5. They want us to classify each critical point as a relative minimum, relative maximum, or neither, justify our answers. So, remember that our derivative is negative 3. Isn't that right? Negative 3? Yeah, negative 3. Negative 3 times 4x minus 7 over 2x squared minus 7x plus 5. And I want to know where this is equal to 0 or where it's undefined, which is where the denominator is equal to 0. So if I have 4x minus 7 equals 0, then x equals 7/4. Over here, if I try and solve this quadratic, I can do this by factoring by grouping. And so I end up with 2x minus 5 times x minus 1. So I end up with x equals 1 or x equals 5/2. Luckily, both of these we don't have to worry about because they're the boundaries of our interval. So what we want to do is we want to understand the behavior of our derivative between, basically around the point 7/4. So I need to test this by taking a look at what happens to my derivative on either side. Keep in mind, I'm sorry, this was supposed to be squared, but that really doesn't matter too much. This is always going to be negative, and this is always going to be positive, which means this expression is really the only thing that determines the sign, the SIGN, of our derivative expression. So if x is less than 7/4, say if x is 1.5, 4 times 1.5 is 6, 6 minus 7 is negative 1, and because my derivative is less than 0, that means that we are decreasing on the interval from 1 to 7/4. And if I try a value that's larger, like 2, that's 4 times 2, which is 8, minus 7, which is 1. So f prime is greater than 0, which means we're increasing from 7/4 to 2.5. So we have a critical point at x equals 7/4 because f prime changes from decreasing to increasing. Now keep in mind, notice I didn't just put a minus sign here and put a plus sign here and say that's my answer. I actually need to put all of these pieces down. I need to say what I know about the derivative, I need to say increasing or decreasing, and I need to specify the interval on which that's happening. I had to do the same thing for this other interval. I didn't just put a plus and say I'm done. I need to actually show work. I actually need to explain using mathematical terminology, not just pluses or minuses. All right, moving on to C, I've got an improper integral. I've got the integral from 5 to infinity of f of x. Now keep in mind, when I'm doing problems like this, I want to change my infinities to some variable and then look for the limit as that variable increases without bound. So I'm looking for the limit as b increases without bound of the integral from 5 to b of my function, 2 over 2x minus 5 minus 1 over x minus 1 dx. So if I'm integrating it, this is a natural log. If I let u be 2x minus 5, then du is going to be 2. And so this comes out to be, again, having to put that limit down. This is going to be the natural log of the absolute value of 2x minus 5 minus the natural log of x minus 1. And I'm evaluating this from x equals 5 to x equals b. Now, this is a natural log difference, so I can combine this into a single natural log. So I'm looking for the natural log, again, limit as b increases without bound, the natural log of 2x minus 5 over x minus 1. And I'm going to do this for x equals b. So as b increases without bound, I've got the natural log of 2b minus 5 over b minus 1 minus the natural log of 2 times 5 minus 5 over 5 minus 1. So, again, remember to close that absolute value. Here, if I take a look at the limit as b approaches infinity, this really becomes the natural log of 2. And this ends up being the natural log of, well, I can leave it as 2 times 5 minus 5 over 5 minus 1. I can leave it like that. I don't have to say natural log of 2 minus the natural log of 5/4, and I don't have to say it's the natural log of 8/5. I've got a numeric answer at this point. It's perfectly reasonable, perfectly valid, and I've evaluated it. It does not diverge. And what's really nice is that this answer is going to help us answer part D. At least it's one way that we can do it. Part D is asking if this Riemann sum, if this sum 3 over 2n squared minus 7n plus 5 converges or diverges. Keep in mind that because f of x is decreasing, approaching 0, then we can use something called the integral test. So since the integral from 5 to infinity of f of x converges, the sum from n equals 5 to infinity of f of n converges. And if you see that, that's great. If you don't see that, there is another way to approach this. This is the first way that I saw this problem. The first thing I notice is that 3 over 2n squared minus 7n plus 5 is always going to be less than 3 over 2n squared for n greater than or equal to 5. Now the thing is, as long as it's for some point past 5, I'm okay. But this is always going to be true because this denominator will always end up being larger. So, doing this calculation, I can say that the sum of 3 over 2n squared converges, again from n equals 5 to infinity. This is going to converge because of the p-test. And because of that, my original sum, 3 over 2n squared minus 7n plus 5, converges by the comparison test. So that's another way that you can look at it without having to do the integral test. Of course, given part C handed it to you on a silver platter, you might as well use it.